Hello everyone, welcome back. Today we are going to talk about AI networking and how the scale matters here. As we all know, AI training is getting scaled, but it requires huge data to be moved from one node to another node. As we all know, the training jobs are distributed within the racks, within the clusters, within the DCs, and even it crosses regions, and now people are talking about the hybrid cloud. So the data has to be moved from one host to another host across the geography location. As we know, the state at which the training model runs has to be captured and saved in a way it can be utilized when there is a failure. The checkpoint data has been tremendously or astonishingly speed grew up with 10x. Last year itself, we have seen checkpoint data were at hundreds of gigs. And this year, we could see that it is like 10x with tens of terabits, and even it has reached to the petabits. As we have seen that, the massive incremental requirement for the larger data, one thought comes in the mind that how it will be handled and what is the bottleneck here while moving the data across the nodes. As the distributed training jobs are relatively known for the failures because there could be a host which is having a problem, there could be a GPU which is running into the problem, and we know that the crashes can happen. But when the crashes happens, there should be a fast recovery, which is also critical for us. The third and foremost important thing is that the hardware is evolving so rapidly. Like every quarter, you might see a different boxes. The question comes in mind that can the AI researcher think about the hardware, or he needs to focus on the software part, the modeling part? So we need to make sure that underlying hardware, without understanding the underlying hardware, how can we run the same model right from the development boxes to the production fleet? The last but not the least is the bootstrapping burst. We all know that the thousands of nodes, the training execution nodes, will be trying to download the parameters, will try to distribute the weights, and all these things will create a thundering herd. It means that there will be a huge connection burst, there will be huge terabits of data movement, and in this situation, the GPU goes idle and the money burns. But all these challenges needs to be understood in the context of the topology. Here we see there are three vertical boxes here. On the rightmost side, there is a backend network. You guys might be familiar with the backend network where the actual training data is going to get moved between the nodes. And on the front-end side, there is a different network which going to act as a control messaging, and whatever the problems we have just described in the earlier slide are going to get mapped into these first two boxes. Now, in the middle box, if you see the host, that is the node where the workers generally perform its operation. As I said, the hardware is evolving. We could see that there is a host with two NICs because one was used to be a failure link. But now, as the data has been moved with the massive scale, we have to use that available link also for the data movement rather than just for the failure purposes. As the evolution has happened, people have migrated from two NICs to the four NICs with the 100 gig. Now we say that, hey, we have a pipe which can be considered as a one flat funnel, and we can make it like a 400 gig. But the evolution is basically not stopping there. It's not only about the number of ports, but it's also about the speed at which it is increasing. So 4 NICs with 200 gig port speed is going to give us the 800 gig funnel. And as we have seen the challenges where the massive data is going to move, we need to understand how this same job runs under the different boxes without changing anything from the model. let's take a deep look into these problems and how these challenges mapped into the topology.
Thanks, Takshak. Let me share a real case to help understand this situation. So not long ago, we received a complaint from one of the training models. The job read latency spiked from 8 seconds to 300 seconds. The root cause was complex, but one key factor stood out. The change of the traffic patterns introduced a surge of backing data within the region, and this leads to the host NIC being overwhelmed. Now let's zoom in on the host to see what's happening there. The GPU server has multiple NICs. If without a special NIC selection solution, the training job on the host is always bound to the first available NIC, which is usually either 0. Now comes the first character, checkpoint. Checkpoint is the saved snapshot of the training job's model status and data. The checkpoint traffic is funneled through this single NIC, while the other NICs are underutilized. But things can get even worse, because data ingestion barges in with truckload of training data, also through the same NIC. The NIC is overwhelmed. This not only slows down the checkpoint performance, but also increase GPU idle time, because GPU is left waiting for the training data to be loaded. And it also has another side effect, hot sparing. Hot sparing is a redundancy technique where the GPU servers constantly receive update data from active jobs so that it can take it over instantly when the primary job failed. This minimizes the job downtime and data loss. Hot sparing depends on the most recent checkpoint. Any delay on checkpoint forces the hot sparing to fall back on older data. This further wastes GPU's compute cycle. Now we have a better understanding of the situation. Takshak will walk through the key technical levers.
Thanks, Yingjie, for summarizing the challenges into the actual topological form. So the summary is very simple. Whether it's a checkpoint IO, whether it's a data injection, if we keep the GPU idle, money is going to get burned unnecessarily. So let's look at how we can utilize the available resources in the best possible or the best optimal way and make sure that our solution is scaling the bandwidth. So far we have said that the bottleneck is the bandwidth, not the compute anymore. And to increase this bandwidth, the first and foremost thing you could see that as the hardware is evolving, we need to make sure that we use all the available resources in the optimal way. We cannot leave any resources just lying over there to save the cost. So if the host is having 1 NIC, utilize it, 2 NICs, utilize it, 4 NICs, utilize it. And that's how we need to make sure that the packet traverser among those 4 NICs should be at the line rate without any compromise. The second and most important thing here is while an application runs, and application could be agnostic to the hardware, it means that without changing any piece of code by the model which is trying to train, the application should utilize all the available resources. The third thing, which also very important, because if we have the bigger hardware, we all know that it is getting divided, the resource is getting divided into the multiple NUMA models. If we have the cross-socket communication, the latency hits and the throughput drops. We have to make sure that the solution what we build is NUMA aware or NUMA smart. The last, whether it is the DC fabric of Meta, whether we basically have the hybrid cloud anywhere, we want to make sure that we don't do any surgeries in the fabric switches. But at the same time, we need to make sure that the hardware what we have at the host level has been utilized correctly. So considering all these 4 checklists, we need to build a solution. So as I said about those 4 points has been divided into 2 parts. One is, of course, the outbound traffic, which is the multi-NIC egress. and then the inbound traffic, which is divided into the ingress part of this agenda. We will also look at the performance impact. We have a lot of wins by implementing these solutions at Meta. So we will talk about the performance impact, as well as there are future advancements. We can make it to build the solution much more smarter. So we will go one by one on this. This is a very quick recap of what Yingjie had showed earlier. Let's take a holistic view of the host. The host, as I said earlier, the NICs has been distributed across the NUMA. You could see that here, ETH0, ETH1, a little bit, ETH2, ETH3 into the separate NUMA. And in Meta, at this point in time, every training workload, inference workload, take any workload, it runs inside the container. And these containers are network separated. It means that the container's network is different than the physical network. So we have to make sure that the container also has exposure to the physical NICs inside it. We do this not using the standard virtual Ethernet driver. If you guys heard about the vEth, we have a netkit, which is a very lightweight Ethernet device, which has been recently built by the kernel team in Linux, and that is what we basically use it here. So this NIC helps us not to have any buffering, but directly access the physical NIC from the container side. As we know that the training model is going to be splitted across so many nodes, they have to communicate with each other. They need to know who are their peers. This peer identification has to have the IP identifier. So we need to make sure that we assign IP addresses to each of these NICs exposed inside the container, as well as the central container IP. We sometimes call it as a task IP, as this is a task of a bigger training job. Now the main thing is, if the training processes which are running inside the container, they have access to each NIC, they can say that, hey, I bind to this NIC and I transfer my data. But if they want to do that, they need to be aware about the underlying hardware. So there are two parts. Application is aware about the NIC. Application is agnostic to the NIC hardware. So our solution talk about both. As I said, that the IPs has been assigned to each and every NIC. They are already available for the processes to be utilized. Or if the processes doesn't want to look into what all the NICs are available, then they can go into our solution, which is ECMP based. It's a simple ECMP setup inside the container with all the NICs has the equal path into it, and that helps to drive the load balancing for the outgoing traffic. The quick part here is we do it at the line rate. We make sure that we have a kernel hook inside the interfaces that drives the packet directly to the physical NIC using the eBPF technology. These are the simple snippets, how we basically set up the multipath. We also have the stickiness at the flow level so that we know that the packet reordering and other challenges will not be there. And with that, I would like to hand over to Yingjie to get into the ingress.
Thanks, Takshak. So let's look at how we can improve the ingress traffic performance. Our network has come a long way. The hardware has been getting faster and faster. Pod bandwidth doubled almost every 2 years. The advanced routing solutions reduce latency and the packet loss down. The hosts are equipped with multiple high-speed NICs. But on the very last hop, we're still going through one single NIC. How do we turn this single trail into multiple lanes? A very instinctive solution is to use the ECMP forwarding from the rack switch to the host so that we can put all the NICs into the play. And that is what we do. To achieve this goal, we introduced 2 key components to the container. First of all, we extend the virtual IP concept. Virtual IP is a logical IP that is not bound to any physical interface. Virtual IP is used for high availability and low balancing. On the container, every job has a dedicated task IP. This task IP is derived from the physical NIC subnet, but we regard it as a virtual IP. Decouple it from the physical NIC. This allows us to associate this task IP with multiple next hops. Secondly, a lightweight BGP peer is installed on the container, which is called Virtual IP Injector or VIP Injector. So this VIP Injector establishes and maintains the BGP session between the container and the rack switch. VIP Injector announces the task IP as a virtual IP to the rack switch with multiple equal cost next hops, and each next hop represents the physical NIC on the host. So an ECMP forwarding table and then is created on the rack switch. When the traffic flow comes to the rack switch, consistent hashing will assign these flows onto dedicated next hops. This way, we spread out traffic evenly among all the available NICs. And there is another advantage of using this BGP-based solution. The rack switch, it can adapt to physical failures without any additional assistance. So when the link goes down, the rack switch can detect this physical failure, and it will remove the corresponding next hop from the ECMP group. When the traffic flow that was previously assigned to this next hop comes in, they will be rehashed and will be assigned to the rest healthy NICs. So we still have a balanced traffic among these NICs without packet loss. This generation of ECMP forwarding table and automatic failover is completely transparent to applications. We know that there are a large number of training jobs running simultaneously in the large AI model. So there is a concern. If we announce every task to the network, will it cause routing churns? Will it overload the routing table? The answer is, if we can manage the address space and aggregation well, this won't be a problem. We use a hierarchical address allocation strategy from the top of the network to the NIC. Starting from the NIC, each layer's address space is fully aggregated by the layer above it. This means that we just need one aggregation route on each layer to reach the NIC. The task IP is also part of the NIC subnet, so it is also aggregated on the rack switch. When VIP Injector announces the task IP onto the rack switch, routing policy on the rack switch will stop the propagation, prevent the route to be leaked to the network beyond the rack. This means we introduced zero actual route to the network beyond the rack. This routing design makes the solution very scalable. And additionally, we introduced security check. This ensures that only this training job can announce this task IP, and it avoids the traffic hijacking of the training data. Now, we have introduced both this ingress and egress solutions. Let's look at the cumulative performance results by applying this bidirectional solution. Do you still remember the case I introduced at the beginning? The job read latency spiked from 8 seconds to 300 seconds. We applied this bidirectional solution to the training job, and we see a substantial reduction from 300 seconds to 1 second. Meanwhile, the checkpoint loading latency also dropped from 800 seconds to 100 seconds. We also ran a stress test on the GPU server with 4 NICs, comparing before and after applying this bidirectional solution. We see that the traffic is distributed among the 4 NICs, and each of the NIC take about 1/4 of the stress load. This means we improve the throughput by 4 times. This solution has been applied to various training models. Along the way, we observed challenges and opportunities that we can improve. So Takshak will share our plan for the future.
Thanks, Yingjie, for summarizing it. As she mentioned that we have a huge performance gain and every solution evolves, we need to see that what are the enhancements we can do it in the existing solution. So this is the plain egress path, what I had showed earlier, where we have the ECMP and we are making sure that the load balancing is happening across the multiple available NICs. But when the packet has been routed through a specific NIC, we need to make sure that that NIC is a NUMA aligned one. Otherwise, the cross-socket communication memory read will happen, and that will impact the latency. So one of the foremost critical things right now we are considering is to a NUMA awareness transparently. In the similar form, we have ingress. As we know that we are using the whip injector kind of concept, which injects the task IP to the rack switch. And the rack switch has the load balancing ECMP path, equal path for all the physical NICs. They cannot be aware about where the flow socket of the processors inside the container is on which NUMA link. So we will not be able to put the NUMA awareness inside the switch, but there are ways to improve the latency, and this is what we are considering here. So when all 4 physical NIC bandwidth are getting utilized, the moment packet hits the host, we will be configuring the hardware RX flow steering in such a way that it assigns the right CPU where the flow socket exists. Once this path established, the next subsequent packets generally get cached over this cached socket, and we will see that the latency is improved. This is where we have the advancement right now. With that, if there are any questions. Thank you.